I think this will be the last video of this quarter for Math 10, and in this video I just want to introduce an important concept in machine learning, which is the concept of regularization. So we saw an image of overfitting here, where the true underlying model is quadratic, but when I try to use a degree 10 polynomial, it overfits the data. And one piece of evidence for that was we rescaled the different columns, and then we saw that with those rescaled columns, we get these very large coefficients for the polynomial regression model that we did. And so here, let's follow this link to the scikit-learn documentation for a new object in scikit-learn called ridge, okay, which stands for ridge regression. And so usually what we are trying to do, or what scikit-learn is doing when we evaluate linear regression, is it is trying to minimize the distance between the true outputs y and our estimated outputs. Okay, so think of this w as the coefficients found by the linear regression, and think of this x as the inputs that we give it. So usually it is trying to find how can we get our linear outputs, how can we get those as close to the true outputs as possible? And so what ridge regression does is, instead of trying to minimize this part where all it cares about is the outputs, it also adds this second term where it is some coefficient times the sum of the squares of the different coefficients. So what this means is the bigger alpha is, which we get to choose, and the bigger the coefficients are, okay, which we do not choose, then the more the penalty is. So this the bigger alpha is, the more this is going to reward having small coefficients. Or another way to say it is the bigger alpha is, the more this will penalize having large coefficients. Okay, let's go back here and let me copy this pipeline again. And let me change this from linear regression to ridge regression. Okay, and it's just written as ridge here. And I need to import it from scikit-learn. So from sklearn, still called linear model, import ridge. Okay, good. And now let's try this with alpha equals 0 and see what happens. And so let me copy this pipe.fit. Okay, and into, let's call it pred 0 to remember that it's alpha equals 0. Let's put a new column into our data frame that is this pipe.predict, and now just dfx. Okay, great. And now let me get my C2 or cpred definition from up here. And so let's see, instead of calling it cpred, let me call it C0 to match the alpha equals 0 here. Okay, black is still fine, and then we want to use pred 0 here. Okay, and then let's look at C plus C0. So it's the exact same as before. And why is that? Well, we're trying to minimize the function that's the usual function plus 0 times something. Okay, so this alpha is not playing any role in this case. So it makes sense that we get the exact same graph as before. Okay, this polynomial curve that's shown in black here. Okay, great. But what happens if I do, for example, so let me save this or copy this. And instead of doing alpha equals 0, let me do alpha equals 10. And then for the fit, let me copy that. Okay, good. And now let me put it into something called pred 10. Or I put it in the wrong place, but that's okay. So here pred 10, and I also overwrote the old pred 0, but that's okay. And then let me copy this. So here, all I should need to change is a couple of these 0s to 10s. Okay, and now let's look at C plus C10. So that's looking a lot better and a lot closer to being quadratic. And you can just see that it's like more regular here. Okay, and that's what regularization tries to do. If I take this pipe and I do named steps, brackets reg, and then I look at the coefficient, it should have fairly significantly smaller coefficients than before. Yeah, so before we were at like negative 4,500 for the last coefficient. Now we're at 1.5 for the last coefficient. And I think the last thing I'll show you is what happens if we overdo the regularization. So for example, what happens if we do alpha much larger? So for example, let's do not 10, but let's do 10,000. So 10 to the 4th. And here we still need to fit again. Okay, and then let's save it again in a new column. Okay, so this is 10,000 here. And now let's make a new Altair chart. And so what you should imagine is that this one is going to be over-regularized, so it doesn't have enough flexibility with its coefficients. And let's save this as C10,000. Okay, and then let's look at this C plus C10,000. So there is what happens if we do too much regularization. It's like there's no flexibility at all anymore, and it looks almost like just a straight line. So those were 3 different examples of different amounts of regularization. Okay, this one where we had 0 regularization, okay, denoted with this alpha equals 0. This one where we had alpha equals 10. And I don't think there's any hard and fast rule for what number is a good number. Okay, and I just tried it before the videos to see what seemed to work well. Okay, then this was with alpha equals 10. Okay, so this was with having a 10 coefficient next to the sums of the squares of the coefficient values. And then this was with going overboard with the regularization, okay, using 10,000 for our alpha coefficient. And this is what the chart looked like in this case. So that video was just a quick introduction to the concept of regularization from machine learning and how to use regularization by using the ridge class in scikit-learn.